Welcome back to the series on topology. In today's video, I'll be discussing Hausdorff spaces, which are special types of topological space in which we can separate distinct points using open sets. You can find a playlist with all the videos in this series by clicking on the info thing that should appear right now. I'm going to start today by giving an example of a space that is not Hausdorff and show that it has some weird properties that we would like to avoid. Consider the space Z, which consists of points 1, 2, and 3, with the following open sets. We always need to include the empty set and the entire space in any topology. And we also include the singleton containing 1 and the set containing 1 and 2. And this will be the topology on this space Z. We can draw a picture of this. Our space has points 1, 2, and 3, and there's an open set containing 1, an open set containing 1 and 2, and finally an open set containing 1, 2, and 3, and there's also the empty set, which doesn't contain any points. Okay, so let's see what's a bit strange about this space. First, we observe that the singleton containing 1 is not a closed set in our space. Why is this? Well, we just applied the definition. We recall that a set is closed if its complement is an open set. But in our case, the complement of the singleton containing 1 is a set containing the points 2 and 3, which we didn't include in our list of open sets. Hence, the singleton 1 is not closed because the set 2, 3 is not open. This is a bit strange if we're used to working with the topology, say, on Euclidean spaces where points are always themselves closed. This is maybe a bit unexpected, but maybe we could live with working with spaces where singletons aren't closed. However, the next point really is something that we would probably like to avoid in almost all cases. So consider the constant sequence at 2. So this is the sequence which has just values 2. And in our space Z, this sequence actually has two different limits. So it has the point 2 and also the point 3 as limits. And this completely goes against our intuition of what a limit of a sequence should be, because obviously this constant sequence at 2 should have 2 as its limit, but in this case it also has another point as its limit. So in this space, limits aren't unique, and this is probably something we want to avoid if we want to keep our intuition of what limit is expressing. To see why both 2 and 3 are limits of the sequence, we need to recall what the definition of a limit of a sequence is in a general topological space. Remember that some point P is a limit of a sequence if for every open neighborhood around P, the sequence, so the elements of the sequence, eventually lie in that open neighborhood, which is another way of saying that there exists some natural number n, such that after the nth element of the sequence, all points lie in the open neighborhood. Using this definition, we can now explain why 2, for example, is a limit of the sequence. Well, we need to look at some arbitrary open neighborhood around 2. And in our case, there are just 2 such open neighborhoods, namely the one containing the points 2 and 1, and also the entire space. And now in both cases, these neighborhoods will always contain 2. So in particular, they'll contain every single element of the sequence. Therefore, the elements of the sequence also eventually lie in every neighborhood around 2. This leads us to conclude that 2 is a limit of the sequence. However, 3 is also a limit of the sequence because the only open set that contains 3 is the entire space. So 3 only has one neighborhood, namely the entire space, and in this case also every element of the sequence lies within the entire space. Hence, by definition, 3 is also a limit of this constant sequence at 2. So what's going wrong here is that for convergence and limits, we're trying to use open neighborhoods around points in order to describe the behavior of these sequences. However, in the case of our space, there is only one open neighborhood around the point 3, namely the entire space. And this open neighborhood is so big that it doesn't allow to distinguish different cases of behavior of this sequence. And this is exactly what leads to the phenomenon that this constant sequence at 2 has 2 limits, namely 2 and 3, because we're trying to define what a limit of a sequence is in terms of open sets, and these open sets in our example of the space Z aren't able to distinguish or separate the points 2 and 3. Maybe another way of saying this is that the open sets we defined don't have enough resolution, so to speak, in order to resolve the differences between the points 2 and 3. We could fix this by including some more open sets in our topology that are capable of separating these 2 points. For example, if we were to also include the set 1, 3, so that's this guy, in our topology, then our problem with the constant sequence at 2 having 2 limits would be fixed, because in this case, 3 would no longer be a limit. Why is this the case? Well, consider this new neighborhood that we've defined around 3, the one containing points 1 and 3. This neighborhood is completely disjoint from this sequence. So no element of the sequence ever occurs in this neighborhood, which means that the sequence also doesn't eventually lie within the neighborhood. So if we include this extra open set 1 and 3 into our topology, then this constant sequence at 2 no longer has 3 as one of its limits. So we've solved the problem of this constant sequence at 2 having these 2 distinct limits. However, our space with this extra open set still doesn't satisfy the property that we can separate 2 distinct points using open sets. This is because any open neighborhood around 2 will still intersect any other open neighborhood around 3. If we wanted to fix that problem, we'd have to include even more open sets into our topology. In any case, I hope this example illustrates what one could mean by talking about separation properties on topological spaces and why they could be important for concrete things like the limits of certain sequences and so on. Now, in general topology, there's a whole list of so-called separation properties of varying strengths. So you can think about the stronger separation properties as being to resolve more things in terms of open sets, and the weaker ones are maybe can only resolve less precise details in terms of open sets. However, in this series, I'm just going to focus on the most important separation property, which is that of being Hausdorff. And how this is defined is what we'll turn to next. A topological space X is called Hausdorff if any pair of distinct points in X have disjoint neighborhoods. So if this is our space X, and we select 2 distinct points P and Q, then if this space is Hausdorff, we can always find some neighborhood around P called UP, and some neighborhood around Q, which I can call UQ, such that these 2 neighborhoods have an empty intersection. We've already seen an example of a space that isn't Hausdorff, so let's see some examples of spaces that are. First off, every metric space is also a Hausdorff space. Recall that a metric space is just some set with a distance function that takes non-negative real values, and this distance function has to fulfill the property that the distance between 2 points is 0 precisely when those 2 points are the same. The distance function has to be symmetric, and also it has to fulfill the triangle inequality. Now, if we have such a metric space, we can put a topology on it by specifying that the open sets just be open balls around any point. So an open ball around some point x of radius r are just all the points that have distance less than r from x. Now, why are metric spaces Hausdorff? Well, if we have some metric space M, and we choose any two distinct points P and Q, these points will be separated from one another by some distance d, which is strictly positive, because the points aren't the same point. We can now consider open balls around these points as neighborhoods. For example, I could choose radius, let's say d thirds, around P, and then look at the open ball around P with radius d thirds. And similar, I could look at the open ball around Q of radius d thirds, and these would be neighborhoods of these 2 points, and they don't intersect. To prove that these don't intersect, one would perform a proof by contradiction. So it would assume that some point would lie in the intersection. Well, then this point would have to have distance from P strictly less than d thirds and a distance from Q strictly less than d thirds. However, these two facts would then contradict the triangle inequality, because the distance between P and Q is d, which is strictly greater than d thirds plus d thirds. In any case, it's pretty clear from this picture that in the metric space, we can just choose these open balls around 2 points, and if we choose the radii to be small enough, these open balls shouldn't intersect one another. Therefore, every metric space is a Hausdorff space, so in particular, Euclidean space Rn is Hausdorff. Maybe as an aside, this statement has an interesting contrapositive, namely that if a space is not Hausdorff, then there's no way to place a metric on that space in such a way that the open sets of that space would be induced by that metric. This process of placing a metric on a space and then having the open sets of that space being induced by the metric, so in terms of these open balls, with respect to that metric, is called being metrizable. So this shows that spaces that aren't Hausdorff aren't going to be metrizable. So in particular, the space we saw at the beginning, because it isn't Hausdorff, there's going to be no way to place a metric on it such that its open sets are induced by that metric. Moving on, let's consider a second example, namely that of a discrete space. And the example is that every discrete space is also Hausdorff. Recall that a discrete space is just a space in which all sets are open sets. So to see why such a space would be Hausdorff, let's take distinct points P and Q in such a space. And now we need to find open neighborhoods of these points that are disjoint from one another. But because the space is discrete, the singleton that just contains P is an open set, and also the singleton that just contains Q is an open set. And these two sets don't intersect one another because P and Q are distinct. So we found a neighborhood of P and a neighborhood of Q that don't intersect, and this shows that this discrete space is Hausdorff. At the beginning of this video, I tried to motivate why we care about the Hausdorff property by showing a non-Hausdorff space which had some weird features. So we would hope now that this property of being Hausdorff would eliminate these undesirable features in general. And the following series of propositions that will prove will show precisely this. Now, the first proposition states that if we have a finite subset of a Hausdorff space, this subset is always going to be closed. In particular, if we have singletons, they'll be closed sets. Let's give a proof of this statement. So we let F be some finite subset of a Hausdorff space X. And now we observe that we can write F as the union over all the singletons containing points in F. Now this is possible for any set. However, in our case, because F is finite, this is going to be a finite union. Now recall that a finite union of closed sets is again a closed set. So it's not the case that arbitrary unions of closed sets are closed. However, finite unions of closed sets are always closed. Therefore, if we can show that these singletons of points in F are closed, we'll have shown that F is closed. All right, so we suppose that F0 lies in F, and P is some point in the complement of the singleton containing F0. So this is just saying that P is some point that is distinct from F0. Now, if no such point exists, then F0 is the only point in the space X, and X is a one-point space, and one can easily check from the definition that a one-point space is always going to be Hausdorff. Thus, we can suppose there's some point P which is distinct from F0, and now we apply the Hausdorff property. So because X is Hausdorff, there is going to exist some open set U that contains F0, and also there's going to exist some open set V containing P with the property that U intersection V is empty. Again, this is just applying the definition of being in a Hausdorff space, because for any two distinct points, we can find neighborhoods around them which are disjoint. Okay, now we observe that U contains the point F0, and U is disjoint from V. So in particular, the set V is not going to contain the point F0. And this fact implies that actually V is a subset of the complement of the singleton F0. In other words, every point of V is not the point F0. All right, now we're almost done. Let's take stock of what's happening. So we found this set V, which is open and is contained in the complement of the singleton F0, and moreover, P is contained in this set V. Now, because P was arbitrary, we have shown the following. For every point P in this set, the complement of the singleton F0, we have found some open neighborhood of that point P that is still completely contained within the set. Now, by a lemma, we saw when we were looking at open and closed sets, this in turn implies that the set X without the singleton F0 is open. Why is this? Well, the reason is that we can just rewrite the original set as a union over all these neighborhoods that we have for each point in the set. Now, because this is a union over open sets, the result will again be open, and the fact that all the neighborhoods are contained in the original set means that using this union, we will recover exactly the original set. In any case, using this lemma, we've shown that this complement of the singleton F0 is open, which means that the singleton containing F0 is closed by definition. And now we're done with the proof, because we've noted up here that we can write F as a finite union over the singletons containing its points. So if every such singleton is closed, we have a finite union over closed sets, which means that F itself is closed. Next, let's turn to limits of convergent sequences in Hausdorff spaces. In our first example, where we looked at a non-Hausdorff space, we saw that there was some sequence there which had two distinct limits. And the following proposition says that such a situation can't occur in a Hausdorff space. So it states that in Hausdorff spaces, convergent sequences have unique limits. That means whenever we have a sequence and it converges to some limit, that limit will be unique. Let's give a proof of this. Let Pi be a sequence in some Hausdorff space X with limit P. Our task is now to show that P is unique. So we suppose, for the sake of contradiction, that we have some point Q, which is distinct from P, is also a limit. Now, because P and Q are distinct points, we can apply the fact that X is Hausdorff to obtain some open set UP that contains P and some open set UQ that contains Q, and these two open sets, UP and UQ, are going to be disjoint. Okay, but this is going to be a contradiction to the fact that the sequence Pi converges to P and also to Q. And to illustrate why this is the case, I'll just draw a little picture. So we have the point P and some open neighborhood UP around P. And then on the other hand, we also have the point Q, which is distinct from P, and we have a disjoint neighborhood UQ around Q. So I'm going to draw the sequence Pi in yellow. And now because Pi converges to Q, there's going to exist some, let's say, natural number NQ, such that for all n greater or equal NQ, we have that Pn lies in UQ. So this is just applying what it means for the sequence Pi to converge towards Q in the specific case where we look at the open neighborhood UQ. So in our picture, Pi will be doing some stuff, but eventually, after NQ, it'll lie completely within UQ. On the other hand, Pi also converges to P, which means there exists some NP, which is a natural number, such that for all n greater or equal NP, Pn lies in UP. So in terms of our picture, again, the sequence will do some stuff, but after this npth element in the sequence needs to lie completely within UP. But now this is a contradictory situation because we have the case that after NP, the sequence lies completely within UP, and after NQ, the sequence lies completely within UQ, but these two sets UP and UQ are disjoint. In particular, if we consider the element of the sequence, which is P, the maximum of NQ and NP, this element should lie both within UP and also within UQ, so it should lie in the intersection. But we said that the intersection was empty, and so this is in fact a contradiction, which proves that our hypothesis that Q is some limit of the sequence which is distinct from P, that this is not possible. So in summary, we've assumed that the sequence Pi has two distinct limits, and we came up with this contradiction. So this shows that convergent sequences in Hausdorff spaces have unique limits. Okay, so this is nice. We've seen that both finite sets in Hausdorff spaces are always closed, and that convergent sequences in Hausdorff spaces always only have a single limit. Now, the final proposition we'll look at concerns limit points of sets in Hausdorff spaces. For this, we suppose that X is Hausdorff and that A is some subset of X. Now, if a point P is a limit point of A, then every neighborhood of P contains infinitely many points of A. To understand this statement, we need to recall what a limit point of a set is. Remember that a point P, which in general it can lie anywhere within X, is a limit point of some subset A of X if every neighborhood around P contains some point of A other than P itself. So if P is a limit point of A, then every neighborhood of P will contain some point of A other than P itself. However, if X is a Hausdorff space, then we automatically get a stronger statement, namely that every neighborhood of P will contain infinitely many points of A. So in particular, it'll contain some point of A other than P itself, but actually it'll contain infinitely many such points. Let's prove this. Rather than writing down the entire proof formally, I'm just going to illustrate it in terms of this picture. So here we have our Hausdorff space X, and we have some subset A of X, and this subset has some limit point P. Now, we want to show that every neighborhood of P contains infinitely many points of A. So we start by choosing some arbitrary neighborhood of P, which I'll call UP. Now we need to show that this neighborhood contains infinitely many points of A. And we'll do so by constructing a sequence of distinct points of A that are all contained within this neighborhood. So first we notice that because P is a limit point of A and UP is a neighborhood of P, this means that there's going to be some point, which I'll call A0, which is distinct from P and that lies within A. And this is going to be the first element of our sequence. Now, because these 2 points are distinct, we are able to apply the Hausdorff property and obtain some open neighborhood around P and an open neighborhood around A0 that don't intersect one another. So I'm going to draw this open neighborhood around P like this. And there's also going to be some open neighborhood around A0 that is disjoint from the open neighborhood around P. But in particular, this means that the open neighborhood around P does not contain A0. Now, because we want all of the points to lie within UP, we have to do this intermediate step where we intersect this new neighborhood we've obtained with UP. This is, again, an open set because the intersection of two open sets is, again, open. So we've found some new neighborhood, which I'll maybe call UP1 of P, which is contained within UP. Now we again apply the fact that P is a limit point of A. So UP1 is a neighborhood of P, and P is a limit point, so this means that there exists some point, which I'll call A1, which lies in A, and which is distinct from P. And this A1 also lies within UP1. Now because UP1 is contained in UP, in particular, A1 also lies in the original UP. Moreover, by the way we've chosen this new neighborhood, UP1 does not contain A0, so A1 will be distinct from A0. Okay, so we've extended the sequence to include another element, and now we just iterate this process that I've been describing. So now we have points P and A1, which are distinct from one another. So again, by the Hausdorff property, we can find some neighborhood around P, which does not contain A1. So maybe this is something like that. Then we again intersect this new neighborhood with the original UP, which means that we obtain some new neighborhood which is contained within UP and also doesn't contain either A1 or A0. And then we again use the fact that P is a limit point to get some point A2 in our sequence, which is distinct from all the other points in the sequence. Now we just continue on in this fashion, and we can do so indefinitely and obtain a sequence which consists of distinct points. Moreover, these points will all lie in the set A because we've obtained them as the result of P being a limit point of A. And finally, these points also all lie within the set UP because we've always intersected these neighborhoods we've obtained via the Hausdorff property with UP. So all of the points will lie in UP as well. Now, this is precisely what we need in order to show the statement, because we've chosen some arbitrary neighborhood UP, and now we've constructed this sequence of distinct points in UP, which also lie in A. And so in particular, UP contains infinitely many points of A. So in summary, we've seen that Hausdorff spaces have several nice properties. First of all finite sets in Hausdorff spaces are closed. Hausdorff spaces have unique limits if sequences converge. And finally, limit points are a much stronger concept in Hausdorff spaces because they fulfill this proposition that every neighborhood of some limit point contains infinitely many points of the set of which it's a limit point. This concludes what I wanted to say about Hausdorff spaces. In the next video, we'll be talking about bases of topologies, which is a tool to describe the topology on a space in terms of certain distinguished open sets.